In this PowerPoint, we're going to apply solubility equilibria to predict when precipitation of certain solids might occur. So precipitation is the reverse of dissolving, and it can be used to provide us with solids that we might need, as in the process described here. Turns out that magnesium ion is readily available in seawater, and the first step in the preparation of pure magnesium metal is the precipitation of magnesium hydroxide from the seawater. So magnesium hydroxide is a sparingly soluble ionic compound, and it is precipitated out by the addition of lime, which is another term for calcium hydroxide, to that water. And calcium hydroxide is a strong base. It's a readily soluble ionic compound that contains hydroxide as the anion. And that means that when it dissolves, it increases the concentration of hydroxide ion. And in terms of the equilibria for magnesium hydroxide, we're increasing one of the products in this particular equilibrium reaction. And that means that increasing a product, the equilibrium shifts to consume that product. And that means that it will shift to the left so that the magnesium ion reacts with the hydroxide and precipitates out as our solid magnesium hydroxide. So if the concentration of magnesium ion in seawater is 0.0537 moles per liter, we want to know if the magnesium hydroxide will precipitate when we add lime to give us a hydroxide ion concentration of 0.0010 moles per liter. Now, in order to figure this out, we're going to do a reaction quotient calculation. This is a calculation of Q. And the first step in this, as in any other type of equilibrium calculation, is to make sure that you have the correct equilibrium reaction, in this case our dissolution equation, and the equilibrium expression associated with it. So this would be our KSP expression, and it is simply the product of our products, magnesium and our two hydroxides. Now, in order to do a reaction quotient, all we do is substitute in the concentrations that we have for magnesium and hydroxide in the seawater and see what we get for Q, see what they give us. Then we compare that Q value to our given KSP to determine in which direction equilibrium will shift. So in this case, we substitute in our concentrations for magnesium, 0.0537, and the concentration given to us for hydroxide, 0.0010 moles per liter. We square the hydroxide according to the equilibrium expression, and you end up with 5.4 times 10 to the negative 8. We compare this to our KSP value. It is much larger than KSP. So remember that when Q is actually larger than K, it means that the reaction will shift towards the reactants to consume some of the product concentration. If Q was less than K, the reaction would actually shift towards the product to produce more of the products. And of course, if Q equals K, that means that your reaction is actually at equilibrium, so there will be no change in the concentrations of either products or reactants. Of course, in this scenario, Q is greater than K. That means we shift towards the reactants, and the reactant is solid magnesium hydroxide. So precipitation will occur in this situation. Let's look at another example. We want to know if potassium perchlorate, KClO4, will precipitate out a solution when we mix 20 milliliters of a 0.050 molar solution containing potassium ions with 80 milliliters of a 0.5 molar solution of perchlorate ions. So with any precipitation problem, we're going to be doing a reaction quotient, but the first step is to actually define the equation involved and the equilibrium expression. Now, since we're given KSP here, this is the reference K that we're always going to find for either dissolving or precipitation. And it's always defined with the dissolving as the forward reaction. So our first step is going to be to write the dissolution equation, which is in the reverse precipitation. So we take our potassium perchlorate as a solid and write what it's actually going to break apart into in terms of ions, our potassium ion and our perchlorate ion as products. We write our equilibrium expression as the product of these ions in solution. And next we want to actually calculate Q and compare it to our KSP that's given to us. Now the trick here is that the reaction quotient Q has to be calculated with the final ion concentrations after mixing. And the concentrations that were given in the problem are actually before we've mixed together our solutions. And once we change the volume of the total solution by combining them together, it will actually change the concentration of the ions that are present. So we need to calculate the final concentration of each of our ions. So for potassium, this is going to be the moles of potassium that are mixed together divided by the final volume of the solution. So the moles of potassium we can calculate simply by taking the volume of the potassium solution that we mix times the concentration, that initial volume and initial concentration. So 0.020 liters for 20 milliliters times that 0.050 moles per liter for the initial molarity. Our liters will cancel out, and it will actually leave us with moles of potassium. We divide this by our new volume of the solution after mixing, so that's going to be our 20 milliliters plus our 80 milliliters of our perchlorate solution, or 0.020 liters plus 0.080 liters. And we divide through by that, and we get our new concentration, our final concentration of potassium ion. We do the same thing with our perchlorate ion, except that for determining the moles of perchlorate, we have to use the volume of perchlorate times the initial concentration of that perchlorate solution. And we get a new concentration after mixing for our perchlorate of 0.40 moles per liter. These are the values that we substitute into our equilibrium expression to solve for Q. So Q then is equal to 0.010 times 0.40, or 4.0 times 10 to the negative third. And this value is less than the KSP for potassium perchlorate. So if our Q value is less than K, that means the reaction shifts towards the products. And if there were solid potassium perchlorate in that solution, it would dissolve. So what this means is that precipitation does not occur. So let's look at one more variation on precipitation. So to prevent blood from clotting, anticoagulants are added to it that actually precipitate calcium ions out. Blood will not clot if calcium ions are removed from the plasma. So some blood collection tubes actually contain salts of the oxalate ion, C2O4, which can react with calcium to form solid calcium oxalate. And what we'd like to know is if you have a concentration of calcium in blood that's 2.2 times 10 to the negative third moles per liter, then what concentration of oxalate ion must be present in order for calcium oxalate to begin to precipitate? So in order for any solid to begin to precipitate in an equilibrium situation, you actually need to get to the solubility limit for that particular substance. And solubility limit, when a solution is saturated, is actually equilibrium. So the solid will not begin to form until we are at the solubility limit, or until our Q value equals K at equilibrium. So what we're really trying to solve for here is to figure out what the equilibrium concentration of our oxalate ion will be if our equilibrium concentration of calcium is 2.2 times 10 to the negative 3 moles per liter. So we're still going to use the equilibrium expression. We're just going to substitute in the concentrations and the KSP value to solve for the concentration that we don't know. And so the first step, of course, is to write that equilibrium expression. So we need to have the dissolution equation for calcium oxalate. So again, we're given KSP, which is always written with dissolving as the forward reaction, precipitation is the reverse. So solid calcium oxalate as the reactant, and our ions, calcium and oxalate ion, as the product. Our equilibrium expression, since it's a 1-to-1 ratio, is just the product of these two ion concentrations. And we're going to substitute into this equilibrium expression the concentration of calcium that we know, as well as the KSP value, and we'll solve for our oxalate ion. So we divide both sides by 2.2 times 10 to the negative 3, and we get an oxalate ion concentration of 1.0 times 10 to the negative 6 moles per liter. So this is the minimum concentration of oxalate ion we need to have in solution in order to start precipitating out the calcium ions. In summary, solubility equilibrium and KSP, or solubility product constants, can be used to predict whether precipitation will occur when certain ions are combined. They can also be used to determine the concentration of ions necessary for precipitation to begin.